I'm Christopher Hollings, and I teach an optional course on the history of mathematics to our third year undergraduates. This is a lecture course followed by a more detailed reading course in which we use primary materials to look at the history of some of the mathematics that the students have met during their first 2 years in Oxford. In these days of pandemic, I've broken the normal 50-minute lectures down into smaller pre-recorded pieces, and so what follows are the two parts of a lecture on the history of complex numbers and complex analysis. This picks up from a quite comprehensive course on complex analysis that the students have done at the beginning of their second year. The main books that I use in the History of Mathematics course are Victor Katz's History of Mathematics and Jacqueline Sale's source book, Mathematics Emerging, and you'll see both of those cited in the video if you're interested in doing some further reading. Hope you enjoy. Right, so having dealt with real analysis in several previous lectures, we now turn at last to complex analysis and also to complex numbers, which we've sidestepped to some extent so far. So this lecture is going to be divided into two parts. The first part is where I will talk mainly about complex numbers themselves and the process of people coming to accept them as valid mathematical entities. And then in the second part, we'll turn to the analysis that started to be done with these numbers in the 18th century, then in particular in the 19th century, and in particular in the work of Cauchy. So we would perhaps argue normally that no field of mathematics is entirely due to one single person, but in the case of complex analysis, that's very nearly true. A lot of the complex analysis that you learn in the Part A course comes from Cauchy's work. Not exclusively, but quite a lot of it. And so, of course, there are topics here that you will have already probably have looked at for the essay for this week. And you may have noticed also that was set up slightly differently from the previous essays in that we had not yet covered this topic in lectures. So that was an opportunity for you to do some digging for material on your own in the same sort of way that you're going to be doing in the reading course next term. Okay, so complex numbers then. We have seen them from time to time in previous lectures, but before 1600 they're only very tentatively identified as mathematical objects. So Cardano noted them in passing in connection with quadratic equations, but didn't do anything with them. Bombelli, who interpreted Cardano, pointed to them in the context of cubic equations and did a few simple calculations with the square root of -1. And as I've already noted, Thomas Harriot was probably the first person to use imaginary numbers systematically in connection with quartic and other equations. But, as it says in Mathematics Emerging, for the most part such roots were ignored. Negative roots were described merely as false, but complex roots as impossible. And this word impossible stuck with imaginary quantities for the next couple of hundred years, even when people were using them and had found that they were not entirely useless, that the name impossible tended to stick to them. So as we'll see in the 17th century, imaginary numbers, complex numbers more generally, were gradually accepted as roots of equations, as necessary roots of equations in order to make certain nice results work, like the fundamental theorem of algebra. But then in the 19th century, they passed to being objects of study in their own right, objects of analysis in their own right. So let's look at the few people on this slide in more detail. So here's Cardano, and he has a problem very much like something you'd find in Diophantus. So find two numbers that add up to 10 and multiply to 40. And what this reduces to is to solving a quadratic equation of the form square plus number equals thing. So square plus constant equals linear term. So of course Cardano had a recipe for this, and when he applied his recipe, he noted that two numbers, perhaps I should have numbers in inverted commas, that crop up are 5 plus or minus the square root of -15. And he dismissed them with this Latin phrase, which has been translated in various different ways, putting aside mental tortures, the cross multiples having cancelled out, or the imaginary part being lost. None of them is a particularly adequate translation, really, and I certainly don't like the last one, because this feels very much like imposing subsequent ideas and terminology on Cardano. But however this is supposed to be translated, he certainly regarded this as a sort of an anomaly that had occurred in the middle of a calculation. It was not something to be pursued any further. It's clearly absurd and of no use whatsoever, so that's where he left things. When Borbély came along a little bit later, he did a bit more with them. So as we see at the top of the slide here, he comments on another sort of cube root, much different from the former. And he develops systematic rules for handling these, which you can see the first part of the list at the bottom of the picture on the slide. So for example, he has a rule that says that the square root of -1 times the square root of -1 is -1, minus the square root of -1 times the square root of -1 is 1, and so on. But like Cardano, he didn't allow complex numbers to be solutions of equations, but he was quite happy for them to appear in the middle of calculations as a computational aid, provided they cancelled out again by the end. So perhaps we're beginning to see the first glimmers of acceptance of complex numbers at this point in the use of complex numbers for practical use, for computational help. And so back again to Harriot. So as I've already said, I think in the lecture, one of the lectures on algebra, his unpublished manuscripts where he's handling polynomial equations make free use of imaginary numbers. You can see them if you look carefully in the middle of this manuscript page. But when parts of his work were published posthumously, these were removed by his editors. So you can have a look at the relevant passages in his work, and also there's an English translation with some commentary where you can look for more information. Early in the 17th century, Descartes commented in passing on imaginary quantities, and in fact coins the word imaginary. In the middle of the picture you can perhaps see him making the contrast between real and imaginary quantities. It's possible that he meant this to be derogatory because he didn't really do anything with them and certainly didn't regard them as numbers. Some efforts to make them into valid objects of mathematical study came about, though, later in the 17th century with the work of John Wallis. So in 1685, Wallis published this text, A Treatise of Algebra, both historical and practical. So it was a historical account of the development of algebra, and it was also a summary of algebra as it then stood. So algebra about solving equations. Wallis had seen Harriot's work in manuscript form, because as I've commented before, it was circulated in manuscript form even before any of it was published. And so there are quite a few remarks in this text of Wallis's where he's essentially accusing Descartes of having plagiarized Harriot. This is one of the major themes of the book. But anyway, when he treats complex numbers, he's trying to justify them by analogy. So he's appealing to Euclidean geometry, he's appealing to trigonometry, he's appealing to properties of conic sections. So, for example, for Wallis, a hyperbola is an imaginary version of an ellipse because you replace a positive square by a negative one, and so on. So this is a little bit like some of the justification that he gave for his early quadrature methods, which I didn't really go into, but he did appeal occasionally to Euclid by way of justification. So certainly he's doing that here. And he starts to build up some analogies for how to understand complex numbers, or imaginary numbers specifically. And he does it by first giving an analogy for negative numbers. So suppose a man starts at a point A and walks 5 yards to a point B, and then retreats 2 yards to C. So overall he's covered 3 yards. So nothing difficult here. It's the sort of thing you've probably met at school. Suppose instead he retreats 8 yards to D. So we might say that he's covered -3 yards. So again, nothing too controversial here. So then Wallis turns to imaginary numbers. So then he says, well, suppose somewhere on a seashore we gain 26 units of land from the sea, but we lose 10. So overall we've gained 16. And if that 16 happens to be a square, then its side would be 4. Alternatively, suppose we lose 26 units and gain 10. So we've lost 16 overall, which means we've gained -16. And if that -16 were a square, then surely it would have side root -16. So that's one of his justifications, one of his analogies. Another one appeals to a classical construction of the geometric mean of two numbers. So AC is the diameter of a circle, PB is a perpendicular to that, and the classical result says that a square built on PB has the same area as a rectangle built on AB and BC. So in other words, that vertical line in the diagram has length root BC. Geometric mean of B and C. And so he adapted this by taking, instead of taking points inside the circle, he took points outside the circle. And so in the diagram on the right, that vertical PB can then be said to have length root minus BC. So here's a page from Wallace. And you can see at the top we've got some geometrical justification of what's happening, and then at the bottom he works through this geometrical construction at the top, which we don't need to worry about, and ends up with numbers or quantities that look like root 175 plus or minus the square root of minus 81. But then he acknowledges that there's something a bit weird going on here and says that this requires a new not a negative root or quantity less than nothing, but the root of a negative square, which in strictness of speech cannot be, since no real root being multiplied into itself would make a negative square. So he acknowledges that this is impossible in some sense, but he's still trying to justify these quantities. On the whole, people were not really convinced because there are certain things in his analogies that you can pick apart. But nevertheless, the idea is beginning to circulate a bit more. So as we enter into the 18th century, we still find comments like this one from Leibniz about the nature of complex numbers. What are these things? But they're increasingly being used. In particular, they're being put together with the brand new calculus and being used as tools there. So, for example, we see transformations where real integrals are converted into imaginary ones, or conversely. So this is sort of a helpful computational tool. If you can't solve a given real integral, then maybe you can substitute a complex variable, do some magic with complex numbers, and then step back into the reals in order to solve this integral. So what I have on the slide now is a page from a paper by Johann Bernoulli. It was published twice, once in French, once in Latin. This is the French version, which looks a lot more like the way we would do mathematics. The Latin version is couched in the language of ratio. But as you can hopefully see, it's quite Leibnizian in its version of calculus. There are lots of differentials on that page. And so what Bernoulli is trying to do is he's trying to solve a particular integral. He's got an integrand a dz over bb plus zz. He makes this substitution that I have on the slide. He transforms it into something involving a square root of minus 1. But if we were to ignore that or just treat it as a constant factor, you see we've got a much easier integral to solve, 1 over t essentially. So this is how he was able to solve this integral by moving to this case and then reversing his substitution. And he really has no worries here, like a lot of other people at this time, about the validity of switching between real and complex integrals. And so the beginning of the 19th century, when people really started to worry about the validity of this is where complex analysis, as we understand it, starts to emerge. Also in the 18th century, or the beginning of the 18th century, we have Newton thinking about complex quantities in his Universal Arithmetic, which is a text on equation solving, essentially, which I mentioned in the algebra lectures. And so for Newton, as you can see from the quotation on the slide, the appearance of complex numbers in any problem that you're working on is a sign that something has gone wrong. So you set up your problem, you work through a solution. If complex numbers appear, it means that your solution was not means that your problem was not set up properly in the first place. So he's using complex numbers as an indicator of real-world solvability of problems. So complex numbers are certainly not solutions in his eyes. Another figure in the 18th century, unsurprisingly, is Euler in his Introductio, which is one of the texts we'll look at next term in the reading course. And so as far as complex numbers are concerned, Euler is taking them and running with them in the same way that he did with the calculus. So he's not worrying too much about the validity of what he's doing, but he's finding that these are very useful tools to use. And so he's using what he knows about calculus, what he knows about power series, and what he knows about complex numbers to unify the elementary functions in this very familiar way that's on the slide. And it's probably in Euler's work that we're starting to get this realization, or we're affirming this realization, that complex numbers are everywhere. And certainly there's a realization that if you want to have this very nice theorem, the fundamental theorem of algebra, then you have to admit complex numbers as solutions of equations. So in the early 17th century, it was certainly known, just by looking at examples, that an equation of degree n can have n roots. And Descartes, I think, was beginning to suspect that an nth degree equation would have exactly n roots if you were to allow complex numbers. And over the course of that century, complex numbers were gradually admitted as roots. And one of the first concrete traces we have of the fundamental theorem of algebra is in a letter of September 1759, which Euler sent to Nicolas Bernoulli, in which he stated the theorem, but he didn't prove it. Around that time, various people, including Euler and some others, were trying to prove it, but the first satisfactory proof came from Gauss in 1799 in his doctoral dissertation, which is a text that contains the seeds of quite a lot of 19th century mathematics. And Gauss, of course, famously proved it once and then proved it lots of other times. Lots of different proofs are available, very similar to his proof of quadratic reciprocity, which we'll mention in passing in a later lecture. In 1806, we get a new proof by Argand, of Argand diagram fame, and then this was made more widely known when Cauchy reproduced this in his 1821 Cours d'Analyse. So Wallis had tried to give a geometrical justification of complex numbers. And by the time we get to the end of the 18th century, beginning of the 19th, people are also starting to think about this again and think about how can we picture these things in order to understand them. So Argand's name is on the slide here, and so it will come as no surprise to you that Argand was one of these people proposing a geometrical interpretation of complex numbers once again. A little before Argand, we have Caspar Wessel, who's a Danish surveyor, who published this text in 1799, in which he treated complex numbers as vectors, and he gave rules for their addition in terms of vectors and so on. So this has relevance not only for the story of complex numbers, but also for the story of the development of the notion of a vector, which we'll come back to in the next lecture on linear algebra. But unfortunately, because this text was published in Danish, it was not well known elsewhere in Europe, and only really became well known when it was translated into French in the 1890s. The famous example, of course, the place where we get our representation of complex numbers from, is Argand in this text of 1806, Essay on a Method of Representing Imaginary Quantities. And so what Argand was doing, and other authors like Wessel were doing at this time, was they were thinking about, suppose positive real quantities lie on a positive real axis, as we would have it. Then if we want to talk about negative quantities, we have to reverse direction, so we go the opposite way. So perhaps it would stand to reason that these complex numbers lie in some other direction. So they start by assuming that we have a real line extending off to infinity in both directions, and then we have some other line coming off of that baseline at an angle. And then they discuss what are the properties that we want our complex numbers to have. And then something that falls out of that discussion is that this line coming off of the real line has to be perpendicular to it. And so then we start to get the idea of imaginary quantities as lying at right angles to the real line. And so Argand and Wessel were not the only people doing this at this time by any means. I could probably fill an entire lecture, possibly more than one lecture, with the efforts of other people at this time to come up with geometrical representations of complex numbers. But they all essentially amount to the version here from Argand, and this is the version from which we derive ours as well. Problems with complex numbers also came up in the context of the British symbolical algebra that I mentioned in the algebra lectures. So there were complaints about the validity of negative numbers, but likewise there were complaints about the validity of complex numbers. And so people in Britain, in the British Isles, were trying to interpret complex numbers in an entirely symbolic way. And so this is what we get from Hamilton. So he defined complex numbers simply to be ordered pairs of real numbers subject to certain rules and operations. This led him in turn to search for a consistent system of triples, which he couldn't find, and then to quaternions, which is something we'll come back to in the next lecture. And so by this point, by the middle of the 19th century, complex numbers are more or less well established as mathematical objects, but there are still some doubts surrounding the validity of making the kind of substitutions in a calculus context that we saw before. And so it's the beginning of the 19th century where people start to worry about these questions, where complex analysis starts to emerge. And so that's what I'm going to turn to in the next part of this lecture.